Welcome back. In the previous lecture, we had contrasted the behavior of thermal and fast neutrons. In this lecture, we will look at the different options available for a nuclear fission reactor. The most important fuel is the isotope of uranium, U-235. The reason for this is even with thermal neutrons, this is a fissionable material. This is, in a way, a big advantage and a disadvantage. Uh, it's an advantage in terms of safety. Okay, so if you look at the natural uranium, it's a mixture of many isotopes. U-235 is present in very small quantity. Okay, the dominant isotope, more than 99%, is U-238. This is not very fission friendly. So in terms of safety, that's a big advantage, but it's a disadvantage in the sense that if you want to use uranium for nuclear fission, you have to separate U-235 from the other components. This aspect of concentrating U-235 is called enrichment. So you have to enrich a uranium fuel to increase the concentration of U-235. So this is an important plot. Let us go through this slowly. What we are plotting on the x-axis is the fission cross-section. The units are in bonds. Note the scale is in log scale. And along the x-axis, the neutron energy is being plotted. So what you see is that for U-235, this is the data for U-235. This is the data for U-238. The fission cross-section is remarkably high. Okay, so it is high, especially at room temperatures. So there are many characteristic features. One is that the reaction cross-section is high at low temperature neutrons and becomes lesser when the temperature of neutron increases. When the energy of neutron increases, the kinetic energy also increases, the temperature of the neutron also increases, and the reaction cross section goes down. So approximately the reaction cross section goes as 1 divided by V, where V is the velocity of neutron. In addition, there are some specific energies where the reaction cross section increases. These are because of certain resonances. We have qualitatively attributed this increase in cross section in some previous lectures to resonances. We won't go into this in greater detail, but that is another feature that has to be noticed. And the reaction cross section keeps going down. In contrast to that, when you look at U-238, in this regime, the reaction cross-section for fission is more or less zero, right? So it is not a fissile material. However, when you have high energy neutron, the reaction cross-section for U-238 towards fission can be increased. But even with such an increase, its overall reaction cross-section is less than what you have for U-235. So this behavior is the main reason why U-235 is the preferred fuel. And whenever you have natural uranium available, you want to be enriching and increasing the concentration of U-235 so that uranium can be utilized for nuclear fission. So in order to sustain U-235 reactor, let's say once you've initiated somehow, you want to sustain it, the sustenance depends upon number of fissile atoms present in the reactor, the cross-section towards fission. The higher the cross-section, the greater is your chance of sustaining uranium fission, and the net neutron that is generated in fission. If you use up all the neutron without generating new neutrons, it is not possible to sustain. But as noted in previous lectures, if you absorb one neutron to initiate fission, overall you are generating 2.42 neutrons. So even when all these excess neutrons are not utilized for fission, a significant part of it is utilized for fission, and that usage helps in sustaining uranium fission. So there are other important fuels. While U-238 is not a fuel per se, when it absorbs a neutron, it generates U-239, and which beta decays into neptunium and eventually into plutonium. Neptunium also beta decays into plutonium. This is an important fuel. It is used for nuclear fission reaction. Therefore, while this is not a fissile nuclei, it is called a fertile isotope. That means upon certain processing, it can give rise to a nuclear fuel. There is another important fuel, especially from Indian context. India, especially the state of Kerala, is very rich in thorium. Okay, so the beaches of Kerala are supposed to have 8 to 10% of thoria. So India has emphasized a lot on how to use thoria as a nuclear fuel. So thoria is also considered a fertile isotope because upon neutron addition and subsequent beta decay, it gives rise to a nuclear fuel, U-233. Okay, so this is a fissile material. So these two are called fertile isotope. Another important concept is called breeding. Okay, so when uranium is used, plutonium can be a byproduct. Okay, so as you saw in this reaction, when you have U-238, it may give rise to U-239 in time. This is a fissile isotope. So when the reactor is operating, while you are using up a fuel, you're also generating a fuel. Okay, so this is a very important feature. So these reactors are called fast breeder reactors. Just to give you an illustration, supposing you take uranium oxide, a solid uranium oxide as a fuel, it is also mixed with plutonium oxide. Okay, so this is a notation for ton. Tani, I think more or less they're approximately 1,000 kgs. Okay, so you start the reactor with fresh fuel. Okay, so you have plutonium and uranium, U-238. So this is not a fuel, but this is a fuel. While the reaction is under operation, some part of U-238 gives rise to plutonium fuel. Okay, so from 3, it becomes 3.25. And of course, there are fission products from the fission of plutonium. Okay, so and U-238 has come down. So this is a spent fuel composition after 1 year. So you stop the reactor, then there are separation process wherein you reprocess this fuel to this composition. So during the operation of the reactor, this is a so-called fast breeder reactor. You have generated a fuel. Okay, so this is an important concept, and a lot of emphasis has been placed in development of this reactor. So here is a schematic of a liquid metal fast breeder reactor. So this component is the same, right? So you have many of the nuclear reactors are close to a heat sink. In most cases, the heat sink is an ocean. For example, it is the coastline of Bombay. We have a lot of reactors. Many are research reactors. And the Fukushima Daiichi, where there was a nuclear catastrophe, was also by the coastline. Unfortunately, tsunami was the reason why it was not a nuclear reactor malfunction, but because of a natural catastrophe, there was a nuclear accident. So typically what you have is that you have a liquid metal. It is usually sodium because sodium has a less cross section for neutron absorption. And sodium is can be melted at a low temperature, and it's a good thermal conductor. So it can take up heat that is being circulated. And eventually that heat from liquid metal is transferred to heat water to steam, and the steam is sent to a turbine which generates electrical energy. And some part of it has to be dissipated because of Carnot limitations. So it is dissipated into, let's say, some ocean body, okay, from water body. This is a heat sink. So this is a fast breeder reactor, fast as we clarified in the previous lecture, because there is no moderator. Therefore, the neutrons have high kinetic energy inside the reactor. So you have a pressure vessel to contain the reactants inside here, and you have a control rods, which can be dropped inside and taken out to control the neutron concentration inside the reactor. So this is a general schematic for a fast breeder reactor. So to re-emphasize, if you have a fast reactor, that means you have fast neutrons because you do not have a moderator. So this is useful for an efficient conversion of U-238 to plutonium fuel. Because there is no moderator, and because the cross-section with respect to fast neutrons is lesser than what you would have had for thermal neutrons, you need to use higher concentration of fuel. So you have 25% plutonium fuel, and this can be bred from U-238. In the next lecture, we will look at an important concept called neutron multiplication, which is critical for sustaining a chain reaction. Thank you.